The universe, vast beyond comprehension, stretches out like an endless, uncharted wilderness, a great dark ocean where the mind struggles to grasp the enormity of space and time. In the silence of the cosmos, humanity has sought for eons to pierce the veil of this infinite abyss. Each step forward is a giant leap into the unknown, yet each discovery, no matter how small, brings us closer to understanding the mysteries that have eluded us for millennia. The very air we breathe, the ground beneath our feet, all of it is born from the stars themselves. And yet, we stand on the precipice, peering into the great expanse with a mixture of awe and terror, knowing that we are but a whisper in the grand orchestra of the universe's existence. The night sky has always been a source of wonder and fear. From the earliest days of humankind, we have looked up, gazing at the stars with a sense of both reverence and helplessness. What are these distant lights, twinkling far beyond our reach? What secrets do they hold? Every culture, across every corner of the globe, has asked these questions, seeking to uncover the answers to mysteries that transcend time, place, and language. Some believed the stars to be gods, others saw them as guides, pointing to distant lands and untold riches. But as humanity's understanding of the world expanded, so too did our sense of wonder at the enormity of the universe. Now, more than ever, our curiosity about the cosmos has become a driving force, a pursuit of knowledge that refuses to be silenced. We have built machines that stretch our senses beyond their natural limits, enabling us to peer deeper into space than ever before. And with each new discovery, the universe seems both more familiar and more alien, offering up new answers but always shrouding them in more questions. The quest to uncover the truth about our place in the cosmos, to understand the very fabric of reality itself, has become one of humanity's most profound endeavors. The story of the James Webb Space Telescope is a testament to that unrelenting drive. A marvel of human engineering, Webb represents the cutting edge of our quest for cosmic knowledge. With its powerful infrared sensors and unparalleled resolution, it promises to peer into the very heart of space, capturing images of the universe that were once unimaginable. Webb's mission is not merely to explore the outer reaches of space but to unlock the secrets of time itself, to look back to the earliest moments of the universe's existence, long before human eyes were even a twinkle in the great darkness of time. It's almost poetic that the Webb telescope will peer into the universe's most distant corners, places where light has taken billions of years to reach us. These distant stars, galaxies, and phenomena are like ancient echoes of a time long past, their light still racing toward us, carrying with it the history of the universe. With Webb's advanced capabilities, we will be able to witness this history in unprecedented detail. But the deeper we look, the more we are confronted by the terrifying idea that the universe is not as we imagined. What will we discover when we peer into the very heart of darkness, into the moments before the stars were born? What truths lie hidden in the depths of space, waiting to be uncovered? These are the questions that keep scientists awake at night, the ones that push them to build instruments like Webb, to take risks and defy the limitations of our current knowledge. As we begin to unravel the universe's most ancient secrets, we may find that we are not prepared for what we uncover. The deeper we dig, the more we realize that the universe is a place of unimaginable complexity, where forces beyond our comprehension are at play. And yet, there is something irresistible about this pursuit, an innate drive to understand no matter the cost. In the silence of space there are whispers of new worlds, new galaxies, new civilizations. These whispers call to us from the deepest recesses of the cosmos, and as we venture further into the unknown, we can't help but wonder, what will we find? Will we uncover the birth of the first stars? Or perhaps, more terrifying still, will we find something far older, far more enigmatic, that will force us to reconsider everything we thought we knew? The story of the James Webb Space Telescope is not just a story of science and technology. It is a story of human ambition, of our endless desire to reach beyond the confines of our earthly existence and touch the stars. It is a story of discovery, of revelations that will forever change our understanding of the cosmos. But it is also a story of fear of what we might find and fear of what we might lose in the process. For every new discovery, every new piece of the cosmic puzzle, brings us one step closer to confronting the unknown. And yet, this fear is not something to shy away from. It is, in many ways, the driving force behind our curiosity. It is the tension between awe and dread that propels us forward, urging us to push the boundaries of human understanding. The unknown is a place of both wonder and danger, a place where the rules of nature as we know them might be turned upside down. It is a place where we might discover the secrets of the universe, or perhaps even something far more terrifying. This is the journey we are on, and with every new revelation we draw closer to the terrifying truth. The more we learn, the more we realize how little we truly understand. The universe is a vast and incomprehensible place, filled with mysteries that have eluded us for centuries. And yet, with every discovery, we inch closer to a deeper understanding of our place in this grand cosmic tapestry. As we venture further into the unknown, one question remains. What is the universe hiding, and will we be ready for the terrifying answers it might reveal? The James Webb Space Telescope is, in many ways, the culmination of decades of scientific ambition and technological innovation. A marvel of human engineering, it represents the pinnacle of our quest to understand the cosmos, to peer further into the darkness of space than ever before. This isn't just another telescope, it is the most advanced space observatory ever built, capable of unlocking secrets that could alter the very way we perceive the universe. Webb is not merely a tool for observing distant stars or galaxies. It is a window into the past, a chance to look back billions of years to the moments after the birth of the universe itself. The telescope is designed to do what no other instrument before it could achieve. It will allow us to witness the universe as it was in its infancy, offering glimpses of the very first stars and galaxies that formed after the Big Bang. At the heart of the Webb telescope's design is its ability to observe the universe in infrared light. Unlike optical telescopes, which capture light visible to the human eye, Webb's infrared capabilities allow it to detect wavelengths that are invisible to us. This is crucial because many of the most distant objects in the universe, including the earliest galaxies, emit light that is stretched beyond the visible spectrum. As light travels across the vast distances of space, it is stretched or redshifted, due to the expansion of the universe. The farther away an object is, the more its light is stretched, moving it out of the visible spectrum and into the infrared range. Webb's infrared sensors are capable of detecting this faint, redshifted light, opening a new window to the universe that was previously closed to us. The telescope's massive, gold-coated mirror, spanning over 6.5 meters, is a work of art and science combined. Made up of 18 hexagonal segments, it is larger and more powerful than any mirror we've ever sent into space. This colossal mirror is designed to capture as much light as possible, gathering the faintest signals from the deepest, most distant parts of the universe. As light from distant stars and galaxies reaches the mirror, it is reflected and focused onto Webb's sensitive instruments, where it is then analyzed to reveal the secrets of the cosmos. This mirror, despite its enormous size, has been carefully constructed to fold up, allowing it to fit into the tight confines of a rocket during launch. Once in space, the mirror unfurls like a delicate flower, ready to begin its mission of discovery. What sets Webb apart from previous telescopes is not just the size of its mirror, but the complexity of its instruments. The telescope is equipped with a suite of scientific tools, each designed for a specific task, from capturing images of distant galaxies to analyzing the composition of exoplanet atmospheres. One of its most powerful instruments, the near-infrared camera, NIRCam, is capable of detecting light from the earliest stars, shedding light on the very beginnings of the universe. Another, the mid-infrared instrument, MIRI, will allow scientists to peer through cosmic dust clouds, revealing hidden stars and galaxies that are otherwise obscured from view. These tools will enable scientists to study everything from the formation of stars and galaxies to the evolution of planetary systems, all with unprecedented clarity and detail. But the Webb telescope's power isn't just in its instruments, it is in the way these instruments work together. The telescope's ability to observe across multiple wavelengths of light, from the near-infrared to the mid-infrared, gives it an unparalleled ability to study the universe in a way that no other telescope can. For instance, it can observe both the heat signatures of planets and the visible light of stars, allowing it to study celestial objects from multiple perspectives simultaneously. This multi-wavelength approach will reveal new insights into the structure and evolution of the universe, offering a more complete picture of how galaxies, stars, and planets form and evolve over time. The journey to get to this point has been anything but easy. The Webb telescope is the result of years of collaboration between scientists, engineers, and technicians from around the world. The project began in the late 1990s, and over the course of more than 2 decades, Webb has undergone countless design revisions, technological breakthroughs, and delays. From its inception, the telescope was designed to be a next-generation observatory that would push the boundaries of what was possible in space exploration. But the road to reality was filled with challenges. The complexity of the design and the high costs of building such a sophisticated instrument meant that every step of the process was fraught with difficulties. Engineers had to find ways to ensure that the telescope could operate flawlessly in the harsh environment of space, where temperatures swing from the searing heat of the sun to the freezing cold of deep space. Perhaps one of the most significant challenges Webb faced was its deployment. Unlike previous telescopes which were launched and assembled in space, Webb's size and complexity meant that it had to be folded up into a compact space before launch. The process of unfurling the telescope once it was in space was an unprecedented feat of engineering. Webb's sunshield, which is about the size of a tennis court, had to be carefully deployed to protect the telescope from the heat of the sun. The telescope's mirror also had to unfold and align itself with extraordinary precision, a task that required the coordination of hundreds of intricate components. If any part of the deployment process failed, it could jeopardize the entire mission. But after years of planning and testing, the telescope successfully unfolded and began its mission of exploration, marking a historic moment in the history of space exploration. Now, as Webb begins its journey through space, it is poised to revolutionize our understanding of the cosmos. With its unprecedented capabilities, it will peer into the very fabric of the universe, shedding light on some of the most profound questions in science. The telescope will search for the first stars that formed after the Big Bang, shedding light on the era of cosmic dawn. It will study the formation of galaxies, star clusters, and planetary systems, offering new insights into how the building blocks of life came to be. It will even study exoplanets, searching for signs of life beyond our solar system. But perhaps the most exciting aspect of Webb's mission is its potential to answer one of the most fundamental questions of all. Are we alone in the universe? Webb's ability to study the atmospheres of exoplanets, to detect the chemical signatures of water, methane, and other molecules, could provide the first real evidence of extraterrestrial life. The possibility that life exists beyond Earth is both thrilling and terrifying, offering the hope of discovering new worlds, but also raising questions about the nature of life itself. What if we find evidence of life out there? What would it mean for humanity's place in the cosmos? The excitement surrounding Webb's mission is palpable, but it is also tempered by a sense of awe and humility. As we peer deeper into the universe, we are confronted with the realization that we are just a small part of a vast, incomprehensible cosmos. The more we learn, the more we realize how much we don't know. Each discovery raises new questions, new mysteries that will take years, if not centuries, to unravel. And yet, it is this very sense of uncertainty that drives us to explore, to reach further into the unknown, to seek answers that may forever elude us. The Webb telescope, with all its sophistication and power, is not just a tool for scientific discovery, it is a symbol of humanity's unyielding desire to understand the cosmos, to make sense of the unfathomable mysteries that lie beyond our reach. In the end, Webb's journey is not just about uncovering the secrets of the universe. It is about pushing the boundaries of human knowledge, about embracing the unknown, and about continuing the quest for answers that has driven us since the dawn of time. As we stand on the edge of this new era of discovery, one thing is clear. We are only just beginning to scratch the surface of the universe's infinite mysteries. And Webb is just the beginning. The origins of the universe are among the most profound and enigmatic questions humanity has ever confronted. For millennia, cultures and civilizations have crafted myths and theories to explain the creation of the cosmos, from the ancient Greeks' notion of an eternal universe to the biblical account of a divine creation. But the modern understanding of the universe's beginnings, grounded in the principles of science and mathematics, is no less awe-inspiring. The Big Bang theory, now widely accepted by the scientific community, posits that the universe began as an infinitely hot, dense point roughly 13.8 billion years ago. From this singularity, space itself began to expand, carrying matter and energy outward, and the universe as we know it was born. This theory is not merely a product of speculation. It is built upon a foundation of hard evidence, observed and verified by astronomers over the course of many decades. The discovery of cosmic microwave background radiation, the faint afterglow of the Big Bang, is one of the key pieces of evidence that supports this theory. This radiation, which permeates the entire universe, is a relic from the earliest moments of the universe's existence, offering a glimpse into a time when the cosmos was still in its infancy. By studying the cosmic microwave background, scientists can trace the origins of the universe and gain insights into its earliest stages, when matter and energy were in a chaotic, primordial state. The very fabric of space and time itself was created in the aftermath of the Big Bang. The universe began as a tiny, hot, and dense singularity, but as it expanded, it cooled, allowing matter to coalesce and form the building blocks of galaxies, stars, and planets. The process of cosmic inflation, which occurred in the first fraction of a second after the Big Bang, played a critical role in shaping the universe as we know it. During this brief but intense period, the universe expanded exponentially, growing by a factor of 10 to the power of 26 in just a tiny fraction of a second. This rapid expansion not only stretched space itself but also smoothed out the irregularities in the distribution of matter, setting the stage for the formation of the first galaxies and stars. Before these structures could emerge, however, the universe was a chaotic and inhospitable place. For the first few 100,000 years, the universe was filled with a hot, dense soup of particles, quarks, electrons and neutrinos, held together by the intense heat and pressure. This period, known as the primordial soup, was a time of violent turbulence, where the forces of gravity, electromagnetism and nuclear interactions were all at play in ways that we can barely begin to understand. But as the universe continued to expand and cool, it reached a point where the first atoms began to form. Hydrogen and helium, the simplest elements, came together to create the first stable matter, and the universe began to take shape. This period of cooling and stabilization allowed light to travel freely through space for the first time. Before this moment, the universe was opaque, filled with dense clouds of particles that scattered and absorbed light. But as the temperature of the universe dropped, these particles combined to form neutral atoms, and the universe became transparent. This moment, known as the decoupling of matter and radiation, marked the end of the cosmic dark ages and the beginning of a new era. The first light in the universe, emitted by these early atoms, began to spread out across space, forming the first cosmic structures. The next stage in the evolution of the universe was the formation of the first stars and galaxies. These early stars were unlike anything we see today, massive, hot, and short-lived. They formed from vast clouds of hydrogen and helium, which collapsed under the influence of gravity to ignite nuclear fusion at their cores. The energy released by this fusion process created the light that illuminated the universe, allowing the first galaxies to take shape. These early galaxies, though small and irregular, served as the building blocks for the larger structures that would come later. The formation of the first galaxies was a pivotal moment in the history of the universe. These galaxies were the crucibles where new elements were created through the process of stellar nucleosynthesis. As stars lived and died, they forged elements like carbon, oxygen, and iron in their cores, enriching the surrounding gas and dust with the building blocks of life. This process continued over billions of years, leading to the creation of more complex stars, planets, and eventually the conditions necessary for life itself. But what is it that makes a star form? How does matter coalesce to create the blazing fires at the center of these celestial bodies? The answer lies in the forces of gravity and pressure. Gravity pulls matter together, causing gas and dust to collapse into dense clumps. As these clumps grow larger and denser, the pressure at their cores increases, heating up the gas and initiating nuclear fusion. This process, which powers stars, also creates the heavy elements that form the foundation of planets and life as we know it. These elements are scattered throughout the universe when stars die, either in supernova explosions or through more subtle processes like stellar winds, enriching the interstellar medium and making the next generation of stars even more complex. 4 billions of years after the first stars formed, the universe continued to evolve, with galaxies merging and forming larger structures. The gravitational pull of these galaxies led to the creation of galaxy clusters and superclusters, the largest structures in the universe. As these galaxies collided and merged, new stars and planetary systems were born. Some of these stars, like our own Sun, would eventually give rise to planets capable of supporting life. But even as we look back on this grand cosmic narrative, we are left with a tantalizing question. What lies beyond the formation of the first stars? What did the universe look like in the moments before these stars ignited? This is one of the central questions that the James Webb Space Telescope is poised to answer. By peering deeper into space than ever before, Webb has the potential to look further back in time, closer to the moment of the Big Bang itself. This is no small feat, as the further we look into space, the further we look into the past, given that light takes time to travel across vast distances. With Webb's advanced infrared sensors, scientists will be able to detect light from the earliest galaxies and stars, offering a glimpse into the universe's most distant past. These observations could provide critical insights into the very birth of the universe, potentially revealing new details about the forces and processes that led to the formation of the first cosmic structures. As Webb begins to collect data from the earliest moments of the universe's existence, we may gain a deeper understanding of how the universe evolved in its infancy. What was it like in those first moments of creation? What forces were at work as the universe cooled and matter began to form? By answering these questions, we will not only unlock the secrets of the universe's birth but also gain a clearer understanding of the processes that continue to shape the cosmos today. From the formation of stars and galaxies to the creation of planets and the potential for life, the story of the universe's origins is a story of complexity, wonder, and endless possibility. The more we learn about the birth of the universe, the more we realize that the universe is a dynamic, evolving system, where every event, no matter how small, ripples through time, shaping the cosmos in ways we can only begin to understand. It is this constant evolution that drives the universe forward, creating the conditions necessary for life, and perhaps, in the distant future, for the emergence of new forms of intelligence and consciousness. The story of the universe's birth is not just a story of the past. It is a story that continues to unfold as we strive to understand the origins of all that exists. And with every new discovery, we move one step closer to uncovering the ultimate truth. How did the universe come to be, and what is its true nature? In the vast expanse of the cosmos, there exists a concept that has long fascinated scientists and philosophers alike: the notion of first light. This term refers to the moment when the universe began to transition from its dark, chaotic infancy to a realm illuminated by the first stars. The birth of these stars marks one of the most profound moments in the history of the universe, signaling the end of the cosmic dark ages and the dawn of a new era. But this first light is not just a poetic metaphor, it is a pivotal moment in the evolution of the cosmos, one that carries profound implications for our understanding of the universe's origins and indeed our own place within it. Before the first stars formed, the universe was a dark and featureless expanse. The Big Bang set the universe into motion, but for hundreds of millions of years, there was no light, no illumination. This era, often referred to as the cosmic dark ages, was a time when the universe was filled with hydrogen and helium gas, swirling in a state of primordial fog. These gases were too sparse and too cold to emit any significant amount of light. The universe, though teeming with particles, was essentially invisible, shrouded in a dense veil of darkness. Yet, despite this darkness, the universe was not static. Gradually, as gravity began to shape the cosmos, pockets of gas began to collapse and condense. Over time, these dense clumps of hydrogen gas grew larger, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. This fusion, the process by which stars are born, marks the moment when first light was born. The first stars were unlike anything we see today. They were enormous, often hundreds of times the mass of our sun, burning with fierce intensity. Their light, though, was not the warm, golden glow we associate with stars today, but instead a fierce blue or ultraviolet hue, far more energetic and intense than what we see in modern stars. These first stars, known as population 3 stars, were not just the first sources of light, they were the very factories where the elements that would eventually form everything from planets to life were created. Through the process of nuclear fusion, these stars began to forge heavier elements like carbon, oxygen, and nitrogen, that are essential for life. These elements would later be scattered across the universe when these stars reached the end of their short, violent lives, either through supernova explosions or other means. In this way, the first stars helped lay the groundwork for the formation of galaxies, planets, and, eventually, life itself. However, the birth of the first stars did not mark the end of the darkness. These stars, though powerful, were few and far between in the early universe, and their light had to overcome vast distances to be seen. It would take billions of years before the light of these early stars spread far enough to illuminate the cosmos on a grand scale. This slow process of cosmic lighting was a gradual unfolding, one that would set the stage for the complex, beautiful structures we see today: galaxies, nebulae, and star clusters. But it wasn't just the formation of stars that would define the dawn of the universe, it was the way that light itself began to alter the very fabric of the cosmos. As the first stars began to shine, they emitted intense radiation that ionized the surrounding hydrogen gas, a process known as reionization. This energy not only illuminated the cosmos but also began to reshape it, breaking apart the hydrogen atoms that had dominated the universe since the Big Bang. The universe, once opaque to light, became transparent as this radiation began to spread. This moment, when the universe transitioned from being a foggy, dense cloud to one that was clear and open to the flow of light, was a turning point in the history of the universe. It marked the end of the cosmic dark ages and ushered in an era of greater complexity. The study of this transition from darkness to light is one of the most exciting areas of research for modern cosmologists. And it is where the James Webb Space Telescope stands poised to make its most groundbreaking contributions. With its unparalleled ability to observe in the infrared spectrum, Webb will be able to peer deeper into the universe than ever before, capturing the faintest traces of light emitted by these first stars. By observing the light from galaxies formed just a few 100 million years after the Big Bang, Webb will be able to uncover new details about the very earliest moments of the universe's history. The importance of Webb's role in this discovery cannot be overstated. Previous telescopes like the Hubble Space Telescope have made remarkable strides in observing distant galaxies and stars, but their capabilities have been limited by the wavelengths of light they can detect. Webb, with its powerful infrared sensors, will be able to penetrate further into the universe, reaching back in time to observe galaxies and stars from the very beginning. This will allow scientists to study the formation of the first galaxies and the first stars in ways that were previously unimaginable. With its sensitivity to infrared light, Webb will be able to study galaxies that are too faint and too distant to be observed by optical telescopes. These distant galaxies are some of the first to form after the Big Bang, and by studying them, scientists can learn about the conditions that existed in the early universe. What were these first galaxies like? How did they form? What kind of stars were they made of? These are the questions that Webb will help answer, giving us a window into a period of time that is both distant and crucial to our understanding of the universe's origins. In addition to studying the first stars and galaxies, Webb's capabilities also allow it to observe the process of reionization in unprecedented detail. By examining the light emitted by distant galaxies, scientists will be able to observe how radiation from these first stars ionized the surrounding hydrogen gas and transformed the universe from an opaque fog to a transparent, light-filled space. This process, which took place over billions of years, fundamentally changed the structure of the universe, paving the way for the formation of the galaxies and clusters of galaxies that we see today. The first light from these early stars holds not just scientific significance but philosophical and existential weight. For in the light of these distant stars lies the story of the universe's birth, the story of how it came to be. Every photon of light emitted by these first stars carries with it information about the conditions that existed at the dawn of time, information that can tell us about the nature of the universe itself. What were the forces at play in those first moments? What physical processes drove the formation of stars and galaxies? By studying these faint, distant traces of light, scientists can piece together the story of the universe's origins, answering questions that have long eluded us. As Webb begins its mission of discovery, we stand at the threshold of a new era of cosmic exploration. The first light from the earliest stars is a beacon, guiding us through the darkness of the past and helping us understand the forces that shaped the universe into what it is today. Through Webb's lens, we can begin to unravel the mysteries of the cosmos, exploring the very origins of the universe, the birth of light, and the forces that shape the universe as we know it. As we gaze into the distant past, we are reminded that we are not just observers of the universe. We are part of its story, and that story is one of light emerging from darkness, of chaos giving way to order, and of a universe constantly evolving, revealing new layers of its vast and infinite complexity. The cosmic dark ages, a period stretching from the Big Bang to the formation of the first stars, represent one of the most mysterious and little understood epochs in the history of the universe. This era, though invisible to the human eye, is crucial to understanding how the universe transitioned from a uniform soup of particles into the complex and structured cosmos we see today. The time before the first stars lit up the sky is, paradoxically, the time when the universe was, in many ways, most active. During this epoch, matter was cooling, gravity was working its quiet magic, and the first seeds of galaxies and stars were beginning to form, all while the universe remained a shadowy and featureless expanse. After the Big Bang, the universe was in a state of chaotic, violent expansion. The hot plasma of particles, protons, neutrons, electrons, and photons, rapidly cooled as space expanded. However, even as the universe grew, the only elements present in any significant quantity were hydrogen and helium, the simplest of all elements. These two gases, which were created in the first few moments of the universe, formed the foundation for everything that would come after. The density of matter during this period was so high that the universe remained opaque, with photons unable to travel freely through space, continually scattering off free electrons in a dense fog. This made the universe invisible to light, and for hundreds of millions of years, there was no visible universe in the way we think of it today. As time passed and the universe continued to cool, gravity began to take hold. The hydrogen and helium gas that permeated the universe slowly began to collapse into dense regions, forming the first dark clouds of matter. These clouds were not yet the brilliant starry clusters we see today, but instead were the raw material for future generations of galaxies and stars. The process by which these clouds of gas collapsed under their own gravity, eventually leading to the formation of the first stars, is one of the most significant and mysterious processes in the history of the universe. It is a moment of great complexity, where the laws of physics, particularly those governing gravity and thermodynamics, dictate the fate of the cosmos. In the absence of light, the universe during the cosmic dark ages was a silent place, with only the slow, gradual process of matter collapsing under gravity moving the cosmos forward. This was a period of profound transformation, even though we can only infer what it was like from the cosmic imprints left behind. The faintest hints of this time, encoded in the cosmic microwave background radiation, provide the only clues we have to what occurred in this murky period. These imprints allow scientists to infer how matter was distributed across the universe and what the conditions were like before the first stars ignited. The end of the cosmic dark ages came with the formation of the first stars, which ended this eerie, lightless epoch and began the process of transforming the universe into a far more structured, illuminated place. The first stars, as massive and hot as they were, began to emit intense ultraviolet radiation. This radiation started a process called reionization, where the previously neutral hydrogen gas was ionized, breaking apart its atoms into charged particles. This marked a dramatic shift in the structure of the universe, as regions of the cosmos that had been opaque for hundreds of millions of years began to clear, allowing light to travel freely across space. This was the moment when the universe for the first time could be seen in the way we understand the universe today, filled with light, radiation, and the energy that would eventually form galaxies, planets, and stars. But the formation of the first stars did not happen overnight. It was not a single moment, but a gradual process that took hundreds of millions of years. During this time, there was no discernible structure in the universe. The regions of matter that collapsed into the first stars were still isolated pockets of hydrogen and helium. These early stars were very different from the stars we see today. They were massive, burning brightly with intense radiation, and they lived short lives. Their massive size and rapid burn rate meant that they consumed their fuel quickly, reaching the end of their life cycles in just a few million years. Despite their brevity, these stars were pivotal in shaping the cosmos, for it was through their death that the elements required for life, elements like carbon, oxygen, and nitrogen, were forged in their cores and scattered across the universe. Their deaths, often in violent supernova explosions, seeded the surrounding gas clouds with the elements that would later form new stars, planets, and even life itself. One of the most fascinating aspects of the cosmic dark ages is the role that gravity played in this process. Gravity is a force that is both subtle and immensely powerful, drawing matter together over vast distances. During this period, gravity slowly gathered the scattered gas into ever-dense pockets, setting the stage for the formation of the first galaxies. These early galaxies were much smaller and more chaotic than the ones we observe today, but they were the building blocks of the larger, more complex structures that would form in later epochs. The collapse of gas into these early galaxies initiated the process of stellar formation, where the gas began to condense into stars. As the first stars were born, they ignited a chain reaction of events that eventually led to the formation of more complex galaxies, clusters of stars, and the intricate cosmic structures we see today. However, despite the importance of this period in cosmic history, much of what occurred during the cosmic dark ages remains a mystery. We know from theoretical models and simulations that the dark ages were filled with dramatic and violent processes. But because the universe was opaque during this period, we cannot directly observe it. Instead, we must rely on indirect methods such as studying the cosmic microwave background and using the most advanced telescopes to look as far back in time as possible. The James Webb Space Telescope, with its unprecedented ability to peer into the infrared spectrum, is poised to provide new insights into this long-hidden era. Webb's instruments will allow us to look further back in time, past the era of the first galaxies, and directly observe the early stages of galaxy formation and the very first sparks of light that ended the cosmic dark ages. The mystery of the cosmic dark ages also speaks to the larger question of the universe's evolution. How did the universe go from a hot, dense plasma to the diverse array of galaxies, stars, and planets we see today? The transition from the dark ages to the era of reionization represents a fundamental shift in the dynamics of the cosmos. The universe moved from a place of opacity to one of transparency, and with that transparency came the light that would shape the universe. This change is not just a transition in the cosmic timeline, it is a transition in the very nature of the universe itself, a shift from a primordial, chaotic state to one of order and structure. Yet, as much as we have learned about the cosmic dark ages, there is still much that remains unknown. What exactly happened during those first few 100 million years? How did the first stars form, and how did they begin to light up the universe? The answers to these questions are hidden in the faintest signals from the past, waiting to be unlocked by instruments like the James Webb Space Telescope. By observing the distant galaxies and stars from the early universe, Webb will help us uncover the mysteries of the cosmic dark ages and bring to light the secrets of the universe's earliest days. In the end, the cosmic dark ages represent a moment of profound transition in the history of the universe. They mark the time when the universe was at its most mysterious, a time when light had yet to illuminate the darkness, and the universe itself was still in its infancy. But these dark ages were not a time of stagnation. They were the crucible in which the first galaxies, stars, and ultimately life itself would form. They are a testament to the power of gravity and the fundamental processes that have shaped the cosmos from the very beginning. As we continue to explore the universe and look deeper into its history, we will begin to piece together the story of the cosmic dark ages, shedding light on this shadowy period and gaining a deeper understanding of the universe's origins. The formation of the first stars, those primordial giants that lit up the cosmos in its infancy, marks one of the most transformative events in the history of the universe. These first stars, known as population 3 stars, were not merely sources of light. They were the cosmic forges where the elements that would later form planets, life, and the very fabric of the universe itself were created. Their birth, life, and eventual death set the stage for everything that followed. They were the architects of the cosmos, laying down the building blocks that would give rise to galaxies, solar systems, and ultimately life as we know it. Before these first stars could shine, the universe had to undergo a long period of cooling. After the Big Bang, the universe was an extremely hot and dense place, filled with a soup of subatomic particles. As it expanded, it began to cool, eventually allowing for the formation of simple atoms, primarily hydrogen and helium. However, it wasn't until about 200 to 400 million years after the Big Bang that the first stars began to form. This delay was due to the fact that gravity, the force that ultimately brought the gas clouds together to form stars, needed time to act on the gas, pulling it together into dense clumps. The first stars were fundamentally different from the ones we see today. They were far more massive, often hundreds of times the mass of our Sun, and they burned with an intensity that is almost unimaginable. Because they were so massive, their life cycles were short, often lasting only a few million years. In comparison, our Sun, which is much smaller, has a life expectancy of about 10 billion years. These first stars were blazing beacons of energy, lighting up the universe in ways that had never been seen before. The process of star formation begins with the collapse of gas clouds under the influence of gravity. In the early universe, these clouds were made primarily of hydrogen and helium, the simplest and lightest elements. Over time, small fluctuations in the density of these gases caused certain regions to collapse more quickly than others. As the gas collapsed, it began to heat up, and once the temperature and pressure were high enough, nuclear fusion ignited in the core, marking the birth of a star. But the conditions for star formation were much more extreme in the early universe than they are today. In the absence of the heavier elements that we find in the gas clouds of modern star formation, these early stars were able to form at a much larger size, as gravity was able to collapse the gas clouds more efficiently. These stars were much hotter and bluer than the stars we see today, burning through their fuel at a much faster rate. The importance of these first stars cannot be overstated. They were not just beacons of light, but cosmic laboratories where the fundamental elements of the universe were created. The process of stellar nucleosynthesis, which occurs inside the cores of stars, is responsible for creating the heavier elements that form everything from planets to life. These elements, such as carbon, oxygen, nitrogen, and iron, were forged in the hearts of these early stars. When these stars eventually died, most of them in massive supernova explosions, they released these elements into the surrounding gas, enriching the universe with the building blocks necessary for the formation of more complex structures. These first stars were also the birthplace of much of the radiation that would help shape the universe. The intense ultraviolet light emitted by these stars ionized the surrounding hydrogen gas, a process that is thought to have played a key role in the reionization of the universe. Before this period, the universe was a vast, dark place, filled with neutral hydrogen gas that absorbed light and blocked it from traveling freely. But the radiation from these first stars ionized the hydrogen, breaking it into protons and electrons and allowing light to travel freely once again. This was a critical moment in the history of the universe, as it marked the end of the cosmic dark ages, and the beginning of a new era, one where light and radiation could once again illuminate the cosmos. The formation of these first stars was also the beginning of the first galaxies. As stars formed, they clustered together, drawn by gravity, forming the first galaxies. These early galaxies were much smaller and less structured than the ones we see today, but they were the seeds from which larger galaxies would eventually grow. The interactions between these early galaxies, including mergers and collisions, played a crucial role in the evolution of the universe, shaping the distribution of galaxies that we observe in the present day. Despite their importance, the first stars were fleeting. Because they were so massive, they burned through their fuel at a rapid pace. After just a few million years, these stars reached the end of their lives, often exploding in cataclysmic supernovae. These explosions were some of the most energetic events in the universe, releasing vast amounts of energy and spreading the elements forged in the stars' cores throughout the universe. The remnants of these explosions, neutron stars and black holes, remained as the lasting marks of the first stars, remnants that continue to shape the universe to this day. One of the most significant consequences of these early stellar explosions was the creation of the first heavy elements. While stars like our Sun primarily produce hydrogen and helium through fusion, more massive stars are capable of fusing heavier elements like carbon, oxygen, and iron. When these massive stars exploded in supernovae, they expelled these elements into the surrounding gas, enriching the interstellar medium with the raw materials necessary for the formation of planets, and ultimately life. This process of stellar nucleosynthesis and subsequent enrichment of the universe is the reason why we and the planets we inhabit are made of the same elements forged in the hearts of long-dead stars. The death of these first stars also provided the raw materials for the next generation of stars. The gas clouds left behind by these supernova explosions began to collapse again under the force of gravity, forming new generations of stars, some of which would be smaller and longer-lived than the first ones. These stars would continue the process of stellar nucleosynthesis, creating more complex elements and eventually forming the building blocks for planets and life. This cycle of star birth and death, of creation and destruction, has been ongoing for billions of years, and it is through this cycle that the universe has become the rich, diverse place that it is today. Despite the crucial role played by these first stars in the evolution of the universe, much of their formation remains shrouded in mystery. Observing the birth of the first stars is a monumental challenge, as these stars formed at such great distances that their light has taken billions of years to reach us. The James Webb Space Telescope, with its ability to observe the universe in the infrared, is designed to help solve this mystery. Webb's powerful instruments will allow scientists to peer back in time to observe the formation of the first stars and galaxies, shedding light on the processes that took place in the earliest moments of the universe. By capturing the faint light emitted by these distant stars, Webb will help answer some of the most fundamental questions in cosmology, including how the first stars formed, what they were like, and how they influenced the evolution of the universe. The formation of the first stars represents a pivotal moment in the history of the universe. These stars were not just sources of light. They were the cosmic laboratories where the elements necessary for life were created. Their death and the subsequent release of these elements into the surrounding gas set the stage for the formation of planets, galaxies, and, ultimately, life itself. Through their intense radiation, they helped ionize the universe, ending the cosmic dark ages and allowing light to travel freely across space once again. The legacy of these first stars is still felt today, as the elements they forged are the same elements that make up everything we see around us. The light they emitted continues to echo through the cosmos, a testament to their profound influence on the universe. As the first stars began to form and illuminate the universe, the next crucial step in the evolution of the cosmos was the emergence of galaxies. These collections of stars, gas, dust, and dark matter would become the fundamental building blocks of the universe, shaping its structure and determining its future. In the earliest stages of the universe, galaxies were small, irregular, and chaotic, but over time, through a series of cosmic processes, they grew larger, more complex, and more structured. Galaxies are not simply random groupings of stars. They are intricate systems governed by the laws of physics, the pull of gravity, and the interplay of forces that have shaped their formation and evolution over billions of years. The formation of galaxies is intricately linked to the birth of the first stars. After the Big Bang, the universe was filled with a vast sea of hydrogen and helium gas, the simplest elements in the periodic table. As gravity began to pull this gas together, it formed dense regions known as dark matter halos. These halos, composed of invisible dark matter, provided the gravitational framework in which galaxies could form. Dark matter, despite its mysterious and elusive nature, played a crucial role in galaxy formation. While it cannot be seen or detected directly, its gravitational influence is felt throughout the cosmos. Dark matter's gravitational pull helped gather regular matter, gas and dust, into dense pockets, creating the first galaxies. These early galaxies were very different from the majestic spirals and elliptical galaxies we see today. They were small, irregular, and often chaotic in structure. The process of galaxy formation was not a smooth or uniform one. Instead, galaxies were constantly evolving, merging, and interacting with one another. These mergers and interactions would ultimately lead to the formation of the larger, more stable galaxies that populate the universe today. The earliest galaxies were likely dominated by the massive, hot stars that formed from the primordial hydrogen and helium gas, and their interactions with each other and with the surrounding gas played a key role in shaping the overall structure of the universe. One of the most fascinating aspects of galaxy formation is the role that feedback mechanisms played in shaping the evolution of these early galaxies. Feedback refers to the process by which the energy and matter produced by stars and black holes influence the surrounding gas and stars. For example, when a star explodes in a supernova, it releases vast amounts of energy into the surrounding gas, heating it up and driving it away from the galaxy. Similarly, the growth of supermassive black holes at the centers of galaxies can release powerful jets of radiation and particles, impacting the surrounding gas and star formation processes. These feedback mechanisms are essential to understanding how galaxies evolve over time and why they take on the structures we observe today. As the first galaxies formed and evolved, they began to interact with one another. Gravity, the fundamental force that governs the motion of all matter, would often cause galaxies to collide and merge. These galactic collisions were violent and chaotic events, but they were also the engine behind the creation of some of the most massive and beautiful galaxies in the universe. When two galaxies collide, their stars rarely collide with one another due to the vast distances between them, but the gas and dust in the galaxies are often forced together, triggering new waves of star formation. These mergers also often lead to the formation of supermassive black holes at the centers of the new galaxies. Over billions of years, these cosmic collisions helped form the more organized, structured galaxies that dominate the universe today. As galaxies grew larger and more complex, the formation of supermassive black holes at their centers became increasingly common. These black holes, which are millions to billions of times the mass of our Sun, are not just remnants of dead stars. They are active, dynamic engines that shape the entire galaxy around them. The formation and growth of these supermassive black holes is still not fully understood, but it is thought that they grew by accreting gas from their surroundings, slowly drawing in matter from the galaxy and growing larger over time. In some cases, these black holes may have formed early in the history of the universe, feeding on the gas and stars around them as galaxies were still in their formative stages. As galaxies formed and evolved, they also began to cluster together, forming groups known as galaxy clusters. These clusters, which can contain hundreds or even thousands of galaxies, are some of the largest structures in the universe. The formation of galaxy clusters is a process that is still ongoing, with galaxies continuing to fall into and merge with clusters over time. The gravitational pull of the dark matter halos within these clusters draws galaxies together, and the interactions between galaxies within clusters can lead to further mergers and evolution. These galaxy clusters, which are often surrounded by hot, diffuse gas, serve as laboratories for studying the interplay between dark matter, regular matter, and the forces of gravity. Over time, the galaxies that formed in the early universe became more structured and more diverse. While the first galaxies were small, irregular, and chaotic, the galaxies that emerged later were more organized, with distinct shapes and features. Some of these galaxies took on the spiral shape we are familiar with today, while others became elliptical or irregular in structure. The variety of galaxy shapes and sizes we see today is a result of the complex processes that took place over billions of years, including mergers, star formation, and the influence of supermassive black holes. The galaxies we see today are not static. They are dynamic systems that are constantly evolving, driven by the forces of gravity, dark matter, and the feedback mechanisms of stars and black holes. One of the most remarkable discoveries in recent years has been the realization that galaxies are not distributed randomly across the universe, but instead form intricate structures. These structures include vast cosmic webs of galaxies, interconnected by threads of dark matter and gas. These cosmic webs are the largest structures in the universe, and their formation is closely tied to the distribution of dark matter. The study of these large-scale structures has provided crucial insights into the nature of dark matter and the forces that govern galaxy formation. Despite the incredible advances in our understanding of galaxy formation, there is still much we do not know. The early stages of galaxy formation in particular remain shrouded in mystery. How did the first galaxies form? What triggered their initial collapse? And what role did dark matter play in their formation? These questions are at the forefront of modern cosmological research, and scientists are turning to the most advanced telescopes, including the James Webb Space Telescope, to answer them. Webb's ability to observe distant galaxies in the infrared allows it to look further back in time than ever before, providing a glimpse into the earliest stages of galaxy formation. By studying the light from galaxies formed just a few 100 million years after the Big Bang, Webb will help scientists unlock the secrets of how galaxies came to be. In addition to its ability to study distant galaxies, Webb's powerful instruments will also allow scientists to study the detailed structure of galaxies in the present-day universe. By observing galaxies at various stages of their evolution, Webb will provide insights into the processes that shape galaxies over time, including the role of dark matter, supermassive black holes, and feedback mechanisms. These observations will help scientists piece together the complex history of galaxy formation, shedding light on the forces that have shaped the universe over billions of years. The story of galaxy formation is not just a story of stars coming together, it is a story of evolution, interaction, and transformation. Galaxies are not static objects. They are living, breathing systems that are constantly evolving, growing, and changing. Their evolution is a dynamic process, shaped by the fundamental forces of the universe. As we continue to observe the distant reaches of space, we are gaining new insights into the formation of galaxies, uncovering the secrets of the early universe, and learning more about the intricate processes that have shaped the cosmos from its very beginning. The galaxies we see today are the result of billions of years of cosmic evolution, and understanding their formation is key to understanding the very nature of the universe itself. As galaxies began to form, so too did the larger cosmic structures that we observe today, the intricate web of galaxy clusters and superclusters that span the universe. These massive structures, formed by the gravitational pull of dark matter and the relentless forces of gravity, represent the largest known objects in the cosmos. The formation of galaxy clusters is a process that involves the interplay of a wide variety of forces, from the collapse of gas and dark matter to the collisions and mergers of galaxies. The evolution of these clusters is a key component in the larger story of the universe's growth and development, and studying them provides vital insights into the fundamental workings of the cosmos. At the heart of every galaxy cluster lies an invisible yet incredibly influential component: dark matter. This mysterious substance, which makes up about 27% of the universe's mass energy content, cannot be seen directly, yet its gravitational effects are undeniable. Dark matter does not interact with light in the way ordinary matter does, which is why it remains so elusive. However, its presence is inferred through its ability to influence the motion of galaxies within clusters. Dark matter creates gravitational wells, which draw galaxies and gas together, facilitating the formation of galaxy clusters. It is this invisible network of dark matter that acts as the scaffolding for the universe's largest structures. Galaxy clusters are not static. They evolve over time through a series of processes that include the accretion of gas, the merging of galaxies, and the interactions between galaxies within the cluster. The formation of a galaxy cluster typically begins with the collapse of a large amount of dark matter, which creates a gravitational potential well. This well then draws in ordinary matter, primarily in the form of hydrogen and helium gas. As this gas falls toward the cluster's center, it begins to heat up, forming a hot, diffuse gas known as the intracluster medium. The intracluster medium is composed of ions and electrons that have been stripped of their atoms, creating a hot, X-ray emitting gas that fills the space between galaxies within the cluster. Over time, galaxies within a cluster begin to interact with one another, undergoing a variety of processes that shape their evolution. One of the most dramatic of these interactions is galaxy mergers. When two galaxies collide, their stars rarely collide directly due to the vast distances between them. However, the gas and dust within the galaxies are compressed and heated, often leading to a burst of new star formation. These mergers also lead to the redistribution of gas within the galaxies, and the eventual formation of supermassive black holes at the center of the newly formed galaxy. These black holes, which can have masses millions or even billions of times that of the Sun, exert an enormous influence on the surrounding gas and stars. In addition to galaxy mergers, interactions between galaxies within a cluster can lead to a variety of other phenomena. One such phenomenon is called ram pressure stripping. As galaxies move through the hot intracluster medium, the pressure from the gas can strip away the outer layers of gas from the galaxies. This process can significantly affect a galaxy's ability to form new stars, as the removal of gas from the galaxy can deprive it of the raw material needed for star formation. Ram pressure stripping is one of the key processes that determines the evolution of galaxies within clusters, contributing to the transformation of gas-rich, star-forming galaxies into gas-poor, quiescent systems. Another significant process within galaxy clusters is the formation of giant elliptical galaxies. These galaxies, which are often found at the centers of clusters, are the result of multiple mergers of smaller galaxies. As galaxies collide and merge, their gas and stars are redistributed, eventually forming a large, elliptical-shaped galaxy. These galaxies are often devoid of the gas and dust that are typically associated with star formation, and their stars are generally older and less active. The formation of these giant elliptical galaxies is a key feature of the evolution of galaxy clusters and is a result of the complex gravitational interactions between galaxies within the cluster. Beyond the galaxies themselves, galaxy clusters also contain vast amounts of hot, X-ray-emitting gas that fills the space between galaxies. This intracluster gas, which makes up a significant portion of the mass in a cluster, is heated to millions of degrees by the gravitational collapse of the cluster. The temperature and density of this gas vary across different clusters, and its study provides important clues about the history and evolution of the cluster. In addition to providing insights into the processes that shape galaxy clusters, the intracluster gas also serves as a powerful probe of dark matter. The distribution and behavior of this gas can be used to map the dark matter distribution within a cluster, helping to shed light on the elusive nature of dark matter. The study of galaxy clusters is a powerful tool for understanding the evolution of the universe as a whole. By observing the distribution, composition, and dynamics of clusters, astronomers can learn about the larger-scale structure of the universe and the forces that have shaped it. One of the most intriguing aspects of galaxy clusters is the role they play in the growth of the universe. As clusters grow through the accretion of galaxies and gas, they also become sites of intense cosmic activity. The interactions within galaxy clusters, such as galaxy mergers, gas stripping, and the formation of supermassive black holes, are responsible for a wide variety of phenomena, including the creation of the most massive galaxies in the universe. One of the most significant aspects of galaxy clusters is the way they serve as a window into the past. The light we observe from distant clusters has traveled for billions of years, allowing us to see these clusters as they were in the early universe. By studying the properties of these distant clusters, astronomers can trace the history of galaxy formation and the evolution of cosmic structures. The James Webb Space Telescope, with its ability to observe distant galaxies in the infrared, will be a crucial tool in this effort, allowing scientists to peer deeper into the universe than ever before and study the formation of galaxy clusters in the earliest moments of cosmic history. In addition to observing galaxy clusters in the distant past, Webb will also provide important insights into the present-day evolution of clusters. By studying the properties of clusters in the local universe, scientists can gain a better understanding of how these massive structures are continuing to evolve. Webb's sensitivity to infrared light will allow astronomers to observe the faintest galaxies within clusters, shedding light on the ongoing processes of galaxy formation, interaction, and evolution. This detailed understanding of galaxy clusters will help to answer key questions about the nature of the universe and its evolution, including the role of dark matter, the processes that govern galaxy formation, and the large-scale structure of the cosmos. As we continue to study galaxy clusters, we are increasingly coming to understand the critical role they play in the universe's evolution. These massive structures are the cosmic laboratories where galaxies form, interact, and evolve. They are the largest known structures in the universe, and their study provides essential insights into the fundamental processes that govern the cosmos. From the gravitational influence of dark matter to the complex interactions between galaxies, the evolution of galaxy clusters is a story of cosmic growth, transformation, and the relentless pull of gravity. The more we learn about galaxy clusters, the more we learn about the nature of the universe itself, and the forces that have shaped it over billions of years. As galaxy clusters grew and evolved, the universe began to display more complex and intricate structures, patterns that could only be explained by the interplay of forces operating on the largest cosmic scales. At the same time, the dynamics within individual galaxies continued to unfold in fascinating ways, with the interaction of gas, dark matter, and stars leading to the formation of the intricate web of galaxies and superclusters we see today. One of the most astonishing discoveries in modern cosmology has been the realization that the universe itself is not randomly distributed but instead forms a vast cosmic web, an intricate, interconnected structure of galaxies, gas, and dark matter that spans billions of light-years. This cosmic web is one of the most striking features of the universe and provides a deep insight into the forces and processes that have shaped its evolution over time. The cosmic web is not just a random collection of galaxies scattered throughout space. It is a highly organized structure, governed by the forces of gravity, dark matter, and the expansion of the universe. At the largest scales, the universe is organized into vast strands of galaxies and dark matter, connected by vast filaments of gas and dark matter. These filaments, often referred to as the cosmic fibers, stretch across the universe, linking together vast clusters of galaxies in a sprawling, interconnected network. These filaments can be thousands of times the size of our own galaxy and represent the largest structures in the universe. The voids between these filaments, regions where there are few galaxies, serve to highlight the intricate pattern of galaxy clustering that permeates the cosmos. The formation of the cosmic web is tied directly to the distribution of dark matter, which, though invisible, exerts a profound gravitational influence on the visible matter in the universe. Dark matter's role in the creation of the cosmic web is central. As the universe expanded following the Big Bang, small fluctuations in the density of dark matter began to form the seeds of larger structures. Over time, these dark matter clumps grew, pulling in normal matter, gas and stars, through gravitational attraction. The result was the formation of a network of galaxies, dark matter and gas filaments, forming the framework of the cosmic web. This cosmic web is not static, however. It is a dynamic and evolving structure, constantly being shaped by the ongoing expansion of the universe, the pull of gravity, and the motion of galaxies through space. Galaxies within the web are not static points, but instead are in constant motion, interacting with one another, merging and colliding. These interactions between galaxies within the cosmic web drive the evolution of the universe on the largest scales. For instance, when galaxies collide, they can trigger bursts of new star formation, altering the structure of the galaxies involved. Similarly, the motion of galaxies through the web can alter the distribution of gas and dark matter, impacting the growth of new cosmic structures. In addition to galaxy mergers, the expansion of the universe itself plays a crucial role in shaping the cosmic web. As the universe expands, galaxies are carried along with it, moving away from each other. This expansion stretches the filaments of the cosmic web, altering their structure and causing the voids between them to become larger. This cosmic expansion, driven by the mysterious force known as dark energy, has been accelerating over the last few billion years, causing the universe's large-scale structures to stretch out even further. One of the key features of the cosmic web is the way in which galaxies and clusters are distributed within it. Galaxies are not evenly spread throughout space, but instead are clustered together in specific patterns. These clusters, often referred to as galaxy superclusters, are massive groups of galaxies bound together by gravity. Superclusters are some of the largest structures in the universe, containing thousands of galaxies. These superclusters are interconnected by the cosmic filaments, forming a vast network of galaxy clusters that stretches across the universe. The distribution of galaxies within these clusters and filaments is not random but is instead governed by the gravitational forces of dark matter and the expansion of the universe. At the heart of many of these galaxy clusters lies the mysterious presence of supermassive black holes. These black holes, which can have masses millions or even billions of times that of our Sun, exert an enormous influence on their surrounding galaxies. Supermassive black holes are thought to form in the centers of most large galaxies, and their growth and evolution are closely tied to the formation of galaxy clusters and superclusters. The energy emitted by these black holes can drive the evolution of the surrounding gas, affecting star formation and the growth of galaxies. Moreover, the gravitational pull of these supermassive black holes can influence the motion of galaxies within clusters, helping to shape the large-scale structure of the cosmic web. The interaction between galaxies, black holes, and dark matter within the cosmic web is a fundamental part of the evolution of the universe. These interactions are not limited to galaxy clusters alone but extend throughout the entire cosmic web. The movement of galaxies through the web can trigger a variety of phenomena, from galaxy mergers to the formation of new black holes. The distribution of dark matter in the cosmic web also plays a crucial role in shaping the motion of galaxies, as it provides the gravitational framework that holds galaxies and clusters together. Despite the significant progress made in understanding the cosmic web, there is still much that remains unknown. One of the biggest mysteries is the nature of dark energy, the force that is driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe's total energy content, but its exact nature remains one of the most profound unanswered questions in cosmology. The expansion of the universe and the stretching of the cosmic web are thought to be driven by dark energy, but the exact mechanics of this process are still not fully understood. Understanding dark energy and its role in the evolution of the cosmic web is one of the key goals of modern cosmology, and scientists are using the most advanced telescopes and observational tools, such as the James Webb Space Telescope, to unlock its secrets. The study of the cosmic web has far-reaching implications for our understanding of the universe. By studying the distribution of galaxies, dark matter, and gas within the web, astronomers can gain insights into the fundamental forces that govern the cosmos. For example, the distribution of galaxies in the cosmic web provides clues about the early evolution of the universe, including the processes that led to the formation of galaxies and large-scale structures. Similarly, the study of dark matter in the cosmic web can shed light on the elusive nature of this mysterious substance, which makes up a significant portion of the universe's mass. Observing the cosmic web at different stages of its evolution allows scientists to trace the history of the universe from the earliest moments of the Big Bang to the present day, providing a deeper understanding of the forces that have shaped the cosmos over billions of years. As our observational tools improve, we are able to peer deeper into the universe than ever before, allowing us to study the cosmic web in unprecedented detail. The James Webb Space Telescope, with its powerful infrared capabilities, will play a key role in this effort, providing insights into the formation of galaxies and the distribution of dark matter in the distant universe. By observing the cosmic web at different wavelengths of light, scientists will be able to study the interactions between galaxies, dark matter, and gas with greater precision, shedding light on the processes that have shaped the universe from its earliest days. Ultimately, the study of the cosmic web is not just about understanding the structure of the universe, it is about understanding the fundamental forces that govern its evolution. From the gravitational pull of dark matter to the expansion of the universe itself, the cosmic web is a manifestation of the deep, underlying processes that have shaped the cosmos over billions of years. As we continue to explore this vast, interconnected structure, we are uncovering the secrets of the universe and gaining new insights into its origins, its future, and our place within it. The cosmic web is a testament to the power of gravity, the complexity of the universe, and the awe-inspiring forces that shape the cosmos. As our understanding of the universe deepens, we realize that the forces driving its evolution are not only vast but also mysterious. One of the most enigmatic forces at play is dark energy, the unknown force responsible for the accelerated expansion of the universe. While dark matter's gravitational influence is felt throughout the cosmos, dark energy operates on an even grander scale, shaping the very fabric of space itself. It is a force so subtle and pervasive that, even though it constitutes around 68% of the total energy content of the universe, it remains largely a mystery. Despite being one of the most significant components of the universe, dark energy is something we cannot directly observe or measure in the traditional sense. Instead, scientists have come to understand its presence through its effects on the universe's expansion and the large-scale structure of the cosmos. Dark energy's impact became apparent in the late 1990s, when two independent teams of astronomers discovered something unexpected. Rather than slowing down over time, the universe's expansion was actually accelerating. This discovery, based on observations of distant supernovae, was a breakthrough that reshaped our understanding of cosmology. Prior to this, it was widely assumed that gravity, the force that pulls objects together, would eventually slow the expansion of the universe, if not halt it altogether. Instead, the discovery of acceleration pointed to an entirely new force, one that opposed gravity and caused the universe to expand at an ever-increasing rate. This realization sparked a race among scientists to understand the nature of dark energy. Unlike dark matter, which exerts a gravitational pull on galaxies and can be detected by its effects on the movement of visible matter, dark energy acts in the opposite way. It pushes matter apart rather than pulling it together, causing the fabric of space-time to stretch. This force, which permeates all of space, has been responsible for the accelerating expansion of the universe for billions of years. However, while its effects are clear, its exact origin and nature remain one of the most pressing questions in modern physics and cosmology. One of the theories that has been proposed to explain dark energy is the concept of the cosmological constant. Introduced by Albert Einstein in 1917 as part of his theory of general relativity, the cosmological constant was initially intended as a fudge factor, to keep the universe static, something that seemed necessary at the time, given that the universe was thought to be unchanging. When it was discovered that the universe was actually expanding, Einstein abandoned the cosmological constant, calling it his biggest blunder. However, with the discovery of the accelerating expansion in the late 20th century, the cosmological constant was revived as a possible explanation for dark energy. In this view, dark energy is a constant energy density that fills space homogeneously, exerting a repulsive force that causes the expansion of the universe to accelerate. While the cosmological constant offers a straightforward explanation, other theories have been proposed that offer alternative views of dark energy. Some scientists have suggested that dark energy could be the result of quantum fluctuations in empty space, tiny fluctuations in the vacuum of spacetime that occur even in the absence of matter. These fluctuations could give rise to the repulsive force we observe as dark energy. Another possibility is that dark energy is a manifestation of a dynamic field, one that changes over time and space, as opposed to the constant energy density suggested by the cosmological constant. This idea, known as quintessence, proposes that dark energy is not a fixed entity but one that evolves in response to the changing conditions of the universe. Despite the many theories, the true nature of dark energy remains elusive. What makes this even more challenging is the fact that dark energy does not interact with light or matter in the same way that other forces do. Unlike gravity or electromagnetism, which can be observed through their effects on visible objects, dark energy's influence is felt only through its impact on the expansion of space. This makes it incredibly difficult to study directly, and our understanding of it relies heavily on indirect observations, such as the measurement of distant galaxies and supernovae, as well as the cosmic microwave background radiation left over from the Big Bang. The impact of dark energy on the universe is profound. As dark energy continues to drive the accelerated expansion of the cosmos, it has significant implications for the future of the universe. One of the most important consequences of this accelerated expansion is the eventual heat death of the universe. As space continues to stretch, galaxies, stars, and eventually all matter will become increasingly isolated from one another. The vast distances between objects in the universe will grow, and the universe will become a colder, darker place. Over time, stars will burn out, galaxies will move beyond our observable horizon, and the universe will continue to expand at an accelerating rate. This chilling scenario is known as the Big Freeze, and it marks one of the possible ultimate fates of the universe. However, while the accelerating expansion seems inevitable, it is important to remember that our understanding of dark energy is still in its infancy. There are still many unanswered questions, and future observations could dramatically change our perspective. For example, the upcoming launch of the James Webb Space Telescope promises to provide unprecedented views of the distant universe, allowing scientists to observe the effects of dark energy on galaxies and other cosmic structures with incredible precision. Webb's ability to observe the most distant objects in the universe, combined with its infrared capabilities, will allow astronomers to peer further back in time than ever before, shedding light on the role of dark energy in the early universe. In addition to its potential to expand our understanding of dark energy, Webb's observations could help scientists answer some of the most fundamental questions in cosmology. For instance, the telescope's detailed observations of distant galaxies could reveal how the universe's expansion has changed over time, providing crucial data on the evolution of dark energy. Additionally, Webb's ability to observe the cosmic microwave background radiation will offer a snapshot of the universe as it was just moments after the Big Bang, potentially providing new insights into the forces that have shaped the cosmos. The search for answers about dark energy is not only a quest to understand the nature of the universe's expansion but also a deeper exploration into the fundamental laws of physics. Dark energy is, at its core, a puzzle that challenges our understanding of space, time, and the forces that govern the cosmos. Its discovery has opened a new chapter in the story of the universe, one that has profound implications for everything from the formation of galaxies to the ultimate fate of the cosmos. While dark energy remains one of the greatest mysteries in modern science, the ongoing efforts of astronomers and physicists promise to bring us closer to understanding the true nature of the universe, and perhaps even uncovering the deeper forces that lie at the heart of reality itself. The exploration of dark energy is not just about understanding the distant future of the universe. It also holds the key to unlocking some of the most fundamental questions about the nature of reality. What is the true nature of space and time? What forces are at play on the largest scales of the cosmos? And how does dark energy fit into the larger framework of fundamental physics? As we continue to probe the mysteries of dark energy, we are likely to uncover new laws of physics and gain a deeper understanding of the universe, its past, and its future. Each new discovery brings us one step closer to answering these profound questions. And as we stand on the cusp of this exciting new era of discovery, we can only marvel at the vast, uncharted territory that remains ahead of us. As our understanding of the universe evolves, we continue to witness the astonishing discoveries and insights brought about by the most advanced scientific tools ever created. One such tool, the James Webb Space Telescope, has emerged as one of the most powerful observatories ever built, poised to unravel the mysteries of the cosmos in ways that were previously unimaginable. Set to revolutionize our understanding of the universe, Webb promises to shed light on a range of fundamental questions about the origins of galaxies, stars, and even life itself. Yet, despite its groundbreaking capabilities, Webb's true potential lies not just in its technological prowess but in its ability to peer back in time, observing the universe as it was billions of years ago, before many of the celestial structures we observe today took form. The journey of understanding the cosmos is one that stretches back to ancient times, with early astronomers gazing up at the night sky and seeking to understand the stars, planets, and the very nature of existence. However, it wasn't until the advent of modern telescopes in the 17th century that our understanding of the universe began to shift. These early telescopes, though rudimentary by today's standards, revealed a universe that was far more expansive and complex than anyone had imagined. With each new advancement in technology, astronomers and physicists have been able to push the boundaries of our knowledge further, culminating in the extraordinary capabilities of modern space observatories like Webb. Unlike its predecessor, the Hubble Space Telescope, which focused on visible and ultraviolet light, Webb is designed to observe the universe in the infrared spectrum. This shift in focus is crucial because infrared light can penetrate cosmic dust clouds that often obscure our view of distant objects. The ability to observe infrared light also allows Webb to peer deeper into the universe, revealing galaxies, stars, and other celestial objects that formed long before we ever thought possible. By observing in the infrared, Webb will be able to uncover the secrets of the early universe, observing the formation of the first galaxies, stars, and even the mysterious first black holes that played such a pivotal role in the evolution of the cosmos. One of the most profound mysteries that Webb will help to unravel is the formation of the very first galaxies. Galaxies are the building blocks of the universe, vast collections of stars, gas, and dark matter that are bound together by gravity. The earliest galaxies were likely small and irregular, formed from the primordial hydrogen and helium left over from the Big Bang. Over time, these early galaxies grew, merging with one another and forming the massive galaxies we observe today. But the exact process by which these early galaxies came into existence remains one of the most perplexing questions in modern cosmology. Webb's ability to observe the universe in the infrared allows it to peer back in time to the first few 100 million years after the Big Bang, a time when galaxies were still in their infancy. By observing the light emitted by these distant galaxies, Webb will provide crucial insights into how galaxies formed, how they interacted with one another, and how the early universe became populated with the structures we see today. Webb will also provide unprecedented views of the formation of stars, the engines of the universe. The process of star formation is one of the most fundamental phenomena in the cosmos, responsible for the creation of the elements that make up everything we see around us. Stars are born from dense clouds of gas and dust, which collapse under their own gravity, triggering nuclear fusion in their cores. The study of star formation is essential to understanding the life cycles of stars, the processes that lead to the creation of planetary systems, and the chemical evolution of the universe. Webb's infrared capabilities will allow it to observe the earliest stages of star formation, including the birth of the first massive stars that helped to light up the universe and the formation of complex molecules that could one day give rise to life. By studying the formation of stars, Webb will help answer fundamental questions about the origins of matter, energy, and life itself. Beyond the formation of galaxies and stars, Webb will also provide insights into the most mysterious and powerful objects in the universe: black holes. Supermassive black holes, which can be millions to billions of times more massive than the Sun, are thought to reside at the centers of most galaxies, including our own. These black holes are not just remnants of dead stars. They are active, dynamic systems that play a central role in shaping the galaxies around them. The formation and growth of supermassive black holes remain a topic of intense study, as scientists try to understand how they formed in the early universe and how they continue to influence the surrounding galaxies. Webb's ability to observe the most distant galaxies and the regions around supermassive black holes will provide critical data on the growth and evolution of these enigmatic objects. Webb's infrared observations will also allow scientists to study the accretion disks surrounding black holes, the swirling masses of gas and dust that are heated to extreme temperatures as they are drawn into the black hole. By studying these disks, scientists hope to learn more about the mechanisms by which black holes grow and evolve. In addition to its ability to peer into the distant past, Webb will also provide insights into the present-day universe, revealing new details about galaxies, stars, and planetary systems. One of the most exciting aspects of Webb's mission is its ability to study exoplanets, planets that orbit stars outside our solar system. Since the discovery of the first exoplanets in the 1990s, scientists have been eager to learn more about these distant worlds and whether they could support life. Webb's advanced instruments will allow it to study the atmospheres of exoplanets in unprecedented detail, detecting the presence of gases like oxygen, carbon dioxide, and methane, which are crucial indicators of potential habitability. By studying exoplanets, Webb will help to answer one of the most profound questions in science. Are we alone in the universe? As Webb continues to collect data and make groundbreaking discoveries, it will undoubtedly raise new questions and challenges for scientists. One of the most exciting aspects of its mission is the fact that it will provide insights not just into what we already know but also into the unknown. Webb's ability to observe the universe in ways that were previously unimaginable will likely lead to new discoveries about the fundamental nature of space, time, and the forces that govern the cosmos. As scientists continue to analyze the data collected by Webb, they will undoubtedly uncover new phenomena, new cosmic mysteries, and perhaps even entirely new fields of study. The impact of Webb on our understanding of the universe will be profound, but it will also be a testament to the power of human curiosity and ingenuity. Webb represents the culmination of decades of scientific discovery, technological innovation, and international collaboration. It is the product of the combined efforts of scientists, engineers, and technicians from around the world, all working together to push the boundaries of our knowledge and understanding. The discoveries made by Webb will not only deepen our understanding of the cosmos but also inspire future generations of scientists, engineers, and explorers to continue seeking answers to the most profound questions about the universe. In many ways, the James Webb Space Telescope represents a new era in space exploration, one in which humanity's ability to look deeper into the universe and further back in time has reached unprecedented heights. With its unparalleled capabilities, Webb will open up new frontiers in our understanding of the cosmos, from the birth of galaxies and stars to the search for life beyond Earth. As we stand on the cusp of this exciting new chapter in our exploration of the universe, we can only marvel at the possibilities that lie ahead and the mysteries that await us in the vastness of space. The James Webb Space Telescope is not just a technological marvel, it is a symbol of humanity's unyielding quest to understand the cosmos and our place within it. As we delve deeper into the cosmos, one of the most profound revelations in modern astrophysics is the discovery that the universe is not just vast and incomprehensibly large, but also intricately interconnected through a network of gravitational forces that bind galaxies, stars, and planets together. The most significant of these forces, gravity, operates on every scale, from the small and intimate to the vast and cosmic. But it is not only gravity that shapes the universe. The interaction between gravity and other fundamental forces of nature, electromagnetism, the weak nuclear force, and the strong nuclear force, determines the very fabric of spacetime itself. The study of gravity has led to some of the most groundbreaking theories in modern physics, starting with Isaac Newton's law of universal gravitation in the 17th century. Newton's theory, which described gravity as a force acting at a distance between masses, was revolutionary at the time and laid the groundwork for understanding the motions of planets, stars, and even entire galaxies. However, as our understanding of the universe grew, so too did the limitations of Newtonian physics. Theories of gravity began to evolve, especially with Albert Einstein's theory of general relativity, which fundamentally changed the way we understand how gravity works. Einstein's theory proposed that gravity is not a force between masses but the result of the curvature of spacetime caused by the presence of mass and energy. This concept, known as the fabric of spacetime, is often likened to a stretched rubber sheet, with massive objects like stars and planets creating indentations or curves in that fabric. The curvature of spacetime dictates how objects move through space, and this is why we observe planets orbiting stars, galaxies moving in clusters, and light bending as it passes near massive objects, a phenomenon known as gravitational lensing. Einstein's general theory of relativity not only provided a more accurate description of gravity but also paved the way for further explorations into the nature of the universe, including the existence of black holes, gravitational waves, and the expanding universe itself. One of the most profound insights that emerged from general relativity was the understanding of black holes, regions of space where gravity is so intense that not even light can escape. The discovery of black holes fundamentally reshaped our understanding of the universe and the extreme conditions that exist within it. These invisible cosmic objects, which can be millions or even billions of times more massive than the Sun, are not just curiosities, they are the engines that power many of the most energetic phenomena in the universe. Supermassive black holes, located at the centers of most galaxies, have a profound impact on their surrounding environments, influencing everything from star formation to the structure of entire galaxies. The growth of these black holes is still not fully understood, but they are believed to grow by accreting matter, gas, dust, and even entire stars, that is drawn into their gravitational pull. The study of black holes also led to the discovery of another mind-bending concept: gravitational waves. These ripples in the fabric of spacetime were predicted by Einstein in 1915, but it wasn't until 2015 that they were directly detected by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are produced by the acceleration of massive objects, such as when two black holes collide. The detection of these waves confirmed a major prediction of Einstein's theory of general relativity and opened up a new way of observing the universe. Gravitational wave astronomy has allowed scientists to hear the universe in a way that was previously impossible, providing new insights into the most extreme cosmic events, from black hole mergers to the collapse of massive stars. In addition to these revelations about gravity, the study of dark matter has played a central role in reshaping our understanding of the universe. While we cannot directly detect dark matter, its presence is inferred through its gravitational effects on visible matter. The most significant of these effects is the way dark matter influences the rotation of galaxies. Without dark matter, the stars and galaxies would not move fast enough to stay bound to the galaxy's center. The fact that galaxies remain intact despite their rapid rotation suggests that there is a substantial amount of unseen matter providing additional gravitational pull. This invisible matter is what we call dark matter. Despite the fact that dark matter cannot be seen, its influence on the motion of galaxies and galaxy clusters is undeniable, and it is believed to make up approximately 27% of the universe's total mass energy content. Dark matter plays a crucial role in the formation of large-scale structures in the universe. Galaxies, galaxy clusters, and even superclusters are all held together by the gravitational pull of dark matter. In fact, dark matter is thought to act as the scaffolding around which visible matter clumps together. Without dark matter, galaxies would not have the mass needed to form or remain bound, and the structure of the universe as we know it would not exist. Yet, despite its importance, we still do not know what dark matter is made of. Scientists have proposed a number of theories, ranging from weakly interacting massive particles, WIMPs, to axions, but the true nature of dark matter remains one of the biggest unsolved mysteries in modern physics. Alongside dark matter, dark energy is another mysterious force that shapes the universe's evolution. Unlike dark matter, which pulls objects together, dark energy acts in the opposite way. It pushes objects apart, causing the accelerated expansion of the universe. While dark matter is responsible for the formation of galaxies and large-scale structures, dark energy drives the rapid expansion of the cosmos on the largest scales. It is thought to make up about 68% of the universe's total energy content, yet it remains largely undetected. The discovery of dark energy in the late 1990s, based on observations of distant supernovae, has radically changed our understanding of the universe's future. Whereas once scientists thought the expansion of the universe would eventually slow and reverse due to gravity, it now seems clear that dark energy is causing the universe to expand at an ever-accelerating rate. These discoveries about gravity, dark matter, and dark energy have revolutionized our understanding of the universe, but they have also led to even bigger questions. How did the universe come into existence? What is the true nature of space and time? And what is the ultimate fate of the cosmos? These questions have become central to modern cosmology, with scientists using a variety of tools and methods to try to unravel the mysteries of the universe's origins and future. One of the most important of these tools is the study of the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang that fills the universe. The CMB provides a snapshot of the universe as it was just 380,000 years after the Big Bang, offering a window into the early universe and providing crucial clues about its evolution. The study of the CMB has revealed a great deal about the early universe, including the distribution of matter and energy and the rate of expansion. By examining the fluctuations in the CMB, scientists can learn about the density of the universe, the amount of dark matter and dark energy, and even the geometry of spacetime itself. The discovery of these fluctuations has provided strong evidence in favor of the theory of cosmic inflation, which proposes that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. This theory helps to explain why the universe appears so homogeneous and isotropic on large scales, despite its vast size. As scientists continue to probe the mysteries of the universe, they are also turning to more advanced technologies, such as the James Webb Space Telescope, to gather more data about the cosmos. Webb, with its powerful infrared capabilities, will allow astronomers to observe the universe in unprecedented detail, revealing the earliest galaxies, stars, and black holes, and helping to shed light on the processes that shape the universe. By studying the formation of galaxies, the growth of supermassive black holes, and the distribution of dark matter, Webb will help answer some of the most fundamental questions in cosmology. The exploration of the universe is not just a scientific endeavor, it is also a philosophical one. The more we learn about the universe, the more we are confronted with questions about our place in it. Are we alone in the cosmos? How did life emerge on Earth? What is the ultimate fate of the universe? These are questions that have fascinated humanity for millennia, and as we continue to explore the cosmos, we find ourselves not only learning about the universe but also reflecting on our own existence. The discoveries we make in the coming decades will not only deepen our understanding of the universe but also inspire us to look inward, asking profound questions about the nature of life, consciousness, and the universe itself. As we continue to explore the cosmos, we are not just uncovering the secrets of the universe, we are also uncovering the secrets of our own existence. The mystery of the universe is not just about the distant stars and galaxies, but also about the very nature of the forces and the materials that make up the cosmos. For centuries, humans have looked up at the night sky with a sense of wonder and curiosity, seeking to understand the laws that govern everything from the tiniest particles to the largest structures in the universe. However, despite all our progress, there remains an unsettling gap in our understanding, an invisible substance that exerts a powerful gravitational force, yet remains completely undetectable by any means other than its effects. This substance, known as dark matter, is thought to make up approximately 27% of the universe's total mass energy content. Yet, it remains one of the most significant and elusive mysteries in modern science. Dark matter's presence became apparent when scientists observed the behavior of galaxies and galaxy clusters. Without dark matter, the laws of physics as we currently understand them suggest that galaxies would not have enough mass to remain intact. In the absence of additional gravitational pull, the stars and galaxies would be moving far too quickly to stay bound to the galaxy. Yet, despite this apparent contradiction, galaxies remain intact, leading scientists to infer the presence of something invisible, but incredibly powerful. Dark matter is thought to provide the additional gravitational pull needed to hold galaxies and galaxy clusters together, acting as the invisible glue that binds the cosmos at large scales. Unlike normal matter, which interacts with light and can be seen through telescopes, dark matter does not emit, absorb, or reflect light. It is completely invisible and interacts with ordinary matter only through gravity. This makes dark matter extremely difficult to detect, and scientists have had to rely on indirect evidence to study it. One of the most important pieces of evidence for dark matter comes from the study of galaxy rotation curves. In a typical galaxy, the outer stars should be moving slower than the inner stars due to the gravitational influence of the galaxy's visible mass. However, astronomers have observed that the stars in the outer regions of galaxies move at the same speed as those near the center, indicating the presence of an unseen mass that is providing additional gravitational force. This invisible mass is what we call dark matter. Another piece of compelling evidence comes from the study of galaxy clusters. When galaxies within a cluster are observed, the light from distant galaxies is distorted by the gravitational pull of the cluster itself, a phenomenon known as gravitational lensing. The amount of distortion observed is far greater than would be expected based on the visible mass of the cluster alone, suggesting that there is a large amount of unseen matter present. This unseen matter is, once again, thought to be dark matter, which is influencing the behavior of light through its gravitational pull. Despite the overwhelming evidence for the existence of dark matter, scientists still do not know what it is made of. The leading hypothesis is that dark matter consists of particles that interact only weakly with ordinary matter, making them extremely difficult to detect. One of the most popular candidates for dark matter is a class of hypothetical particles known as weakly interacting massive particles, or WIMPs. WIMPs are thought to be heavy particles that interact with ordinary matter only through the weak nuclear force and gravity. If WIMPs exist, they would be able to pass through normal matter without interacting with it in most cases, making them extremely hard to detect. However, their gravitational effects on large-scale structures in the universe make them a leading candidate for dark matter. In addition to WIMPs, scientists have also proposed other possible candidates for dark matter, such as axions and sterile neutrinos. Axions are hypothetical particles that are thought to be extremely light and interact very weakly with ordinary matter. They were initially proposed as a solution to a problem in particle physics related to the strong nuclear force. Sterile neutrinos, on the other hand, are a theoretical type of neutrino that does not interact through the weak nuclear force, but instead interacts only through gravity. These particles could account for the missing mass in the universe, but like WIMPs, they have yet to be directly detected. The search for dark matter has become one of the most important endeavors in modern physics and astronomy. Researchers around the world are using a variety of methods to try to detect dark matter, from experiments conducted deep underground to space-based observatories. One of the most promising methods for detecting dark matter is through the use of large particle detectors, which are designed to detect the rare interactions between dark matter particles and ordinary matter. These experiments are often conducted deep underground to shield them from cosmic radiation, which could interfere with the results. One of the most well-known of these experiments is the Large Hadron Collider, LHC, at CERN, which is capable of colliding particles at extremely high energies to recreate conditions similar to those that existed just after the Big Bang. The LHC could potentially produce dark matter particles, which could then be detected by sensitive instruments. In addition to particle detectors, scientists are also looking for dark matter by studying the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. By analyzing the tiny fluctuations in the CMB, researchers can gain insights into the distribution of dark matter in the early universe. These fluctuations provide valuable information about the density and temperature of the universe during its infancy, and they can help scientists understand how dark matter influenced the formation of galaxies and large-scale structures. Another approach to studying dark matter is through the observation of galaxy clusters and the phenomenon of gravitational lensing. As mentioned earlier, the light from distant galaxies is distorted by the gravitational pull of galaxy clusters, allowing scientists to map the distribution of dark matter in these clusters. The gravitational lensing effect provides a way to indirectly see dark matter by observing how its gravity bends the light from more distant objects. By measuring the amount of lensing, astronomers can estimate the mass of the dark matter in a given region, providing important clues about its nature. The study of dark matter is not just about understanding the composition of the universe, but also about understanding the fundamental laws of physics. Dark matter challenges our understanding of particle physics and forces scientists to rethink some of the most fundamental assumptions about the nature of matter and energy. Its discovery has opened up new avenues of research and has the potential to revolutionize our understanding of the universe at the most basic level. However, the search for dark matter is not without its challenges. The most significant of these is the fact that dark matter interacts only through gravity, making it incredibly difficult to detect directly. As a result, scientists have had to rely on indirect evidence and complex simulations to study dark matter's behavior. Furthermore, the current models of dark matter are based on the assumption that it is made of particles that are different from the particles that make up ordinary matter. If this assumption turns out to be incorrect, it could have profound implications for our understanding of the universe. Despite these challenges, the search for dark matter continues to be one of the most exciting and important areas of modern science. As new technologies and experimental techniques are developed, scientists are getting closer to unlocking the secrets of dark matter and understanding its role in the evolution of the universe. Whether it is through particle detectors, astronomical observations, or theoretical breakthroughs, the discovery of dark matter will undoubtedly be one of the most significant milestones in the history of science. In many ways, the search for dark matter represents the cutting edge of human curiosity, a quest to understand the universe on a scale that transcends anything we've ever known before. And as we continue to explore this dark and elusive component of the cosmos, we may just be on the brink of discovering one of the most profound truths about the nature of reality itself. The search for life beyond Earth is one of the most profound and ambitious quests in the history of science. For centuries, humanity has wondered whether we are alone in the universe, gazing up at the night sky and imagining the possibility of distant worlds teeming with life. This question is not just a matter of curiosity, it strikes at the very core of our understanding of existence, the nature of life itself, and our place in the cosmos. As we continue to explore the universe with ever more advanced technology, the question of extraterrestrial life has evolved from a philosophical musing to a scientific pursuit, one that is now grounded in evidence, exploration, and innovation. The search for life elsewhere in the universe is predicated on a number of key assumptions, one of the most important being that the ingredients for life are not unique to Earth. The basic building blocks of life, organic molecules, water, and an energy source, are thought to be ubiquitous in the cosmos, spread across vast regions of space and time. This assumption has been bolstered by the discovery of numerous exoplanets, planets orbiting stars outside our solar system, that appear to be in the habitable zone, the region around a star where conditions might be right for liquid water to exist. Water, as we know, is essential for life as we understand it, and the discovery of exoplanets in the habitable zone has raised the tantalizing possibility that these distant worlds could harbor life, or at least the potential for it. In addition to the discovery of exoplanets, recent advancements in the field of astrobiology, the study of life in the universe, have provided compelling evidence that life may be more common than previously thought. One of the most exciting discoveries came from the observation of extremophiles, organisms that thrive in some of Earth's harshest environments, such as deep-sea vents, acidic hot springs, and the frozen tundra. These organisms have expanded our understanding of the conditions under which life can exist, showing that life can endure in environments that were once thought to be inhospitable. If life can survive in such extreme conditions on Earth, it raises the possibility that life could exist in similarly extreme environments on other planets and moons, where liquid water might exist beneath icy crusts or in subterranean lakes. The discovery of extremophiles has also changed the way scientists think about the potential habitability of other worlds. For example, one of the most promising places to search for life within our solar system is Europa, one of Jupiter's moons. Europa is covered by a thick layer of ice, beneath which scientists suspect there may be an ocean of liquid water. The conditions on Europa may be similar to those of Earth's deep-sea vents, where life flourishes without sunlight, drawing energy from the planet's internal heat. If life can exist in such an environment, then Europa could be a prime candidate for harboring alien life. Similarly, Saturn's moon Enceladus has been found to have plumes of water vapor erupting from its icy surface, suggesting the presence of liquid water beneath the surface. These discoveries have propelled Europa and Enceladus to the forefront of the search for extraterrestrial life, and missions to explore these moons are already in the works, with the goal of determining whether life exists, or ever existed, on these icy worlds. Beyond our own solar system, the discovery of thousands of exoplanets in recent decades has opened up new avenues for the search for life. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our understanding of exoplanets by detecting thousands of planets orbiting distant stars. Some of these planets are located in the habitable zone of their stars, where conditions might be conducive to life. The discovery of these exoplanets has fueled speculation about the potential for life on worlds far beyond our solar system. In particular, scientists are focused on Earth-like planets, rocky planets with the right size, temperature, and conditions to support liquid water on their surfaces. These Goldilocks planets, as they are sometimes called, represent the best candidates for harboring life, as they are similar in many ways to Earth, which has supported life for billions of years. One of the most significant discoveries in the search for exoplanets came in 2015, when astronomers detected an Earth-sized planet orbiting in the habitable zone of a star just 4.2 light-years away. The planet, known as Proxima b, is the closest potentially habitable exoplanet to Earth and has sparked intense interest in the scientific community. While much remains to be learned about Proxima b, its discovery has brought us one step closer to finding a world that could potentially harbor life. Future missions, such as the James Webb Space Telescope, are expected to provide more detailed observations of exoplanets like Proxima b, analyzing their atmospheres for signs of water, oxygen, methane, and other gases that might indicate the presence of life. However, the search for life beyond Earth is not without its challenges. One of the primary obstacles is the vast distances involved. Even the closest stars are light-years away, meaning that even if we detect an Earth-like planet orbiting a distant star, it would be incredibly difficult to send a probe or spacecraft to investigate. Current technology would take tens of thousands of years to reach the nearest stars, making direct exploration of exoplanets impractical in the foreseeable future. Instead, scientists are relying on indirect methods to search for signs of life, such as studying the chemical composition of exoplanet atmospheres, detecting biosignatures like oxygen or methane, and searching for patterns in the light from distant stars that could indicate the presence of intelligent civilizations. One of the most promising approaches to the search for extraterrestrial life is the search for technosignatures, evidence of advanced civilizations. Just as we detect the presence of life on Earth by observing its effects on the environment, such as the oxygen in the atmosphere, scientists believe that we could detect the signatures of other civilizations by looking for artificial signals or pollutants in the atmospheres of distant exoplanets. The search for technosignatures is still in its infancy, but it represents an exciting frontier in the search for life beyond Earth. Projects such as the Breakthrough Listen initiative, which aims to scan the entire sky for signals from extraterrestrial civilizations, are helping to expand the possibilities for detecting intelligent life in the universe. Despite the challenges, the search for life beyond Earth continues to captivate the imagination of scientists, philosophers, and the general public alike. The discovery of even microbial life on another planet would have profound implications for our understanding of biology, the origins of life, and our place in the universe. It would also force us to reconsider the uniqueness of Earth and our role as stewards of life on this fragile planet. But the search for life is not just about finding other civilizations. It is about understanding the conditions that allow life to exist, the potential for life to evolve in different environments, and the broader implications for the future of humanity. The discovery of life elsewhere in the universe, no matter how small or simple, would be one of the most profound achievements in the history of science. It would not only answer one of the most fundamental questions humanity has ever asked, but it would also have a transformative impact on our worldview. It would challenge our ideas of life, intelligence, and existence, and invite us to reconsider our place in the cosmos. The search for life beyond Earth is not just a scientific endeavor, it is a deeply philosophical quest, one that speaks to our deepest hopes and fears, our insatiable curiosity, and our drive to understand the mysteries of the universe. And as we continue to explore the stars, the question of whether we are alone in the universe remains as relevant as ever, propelling us toward a future where the answers we seek may one day be within our reach. The quest to understand the universe is, at its core, a search for answers to some of the most fundamental questions about existence itself. For centuries, humans have gazed up at the stars, wondering about the origins of the cosmos, the nature of time and space, and the forces that govern the workings of the universe. But it was not until the 20th century that science began to answer these questions with any degree of certainty. The development of modern cosmology, driven by breakthroughs in both theory and technology, has led to the creation of a unified framework that seeks to explain the origins, evolution, and eventual fate of the universe itself. However, even as we piece together this grand narrative, we are confronted with new, even more profound questions, ones that challenge our understanding of the very fabric of reality. The birth of cosmology as we know it began with the formulation of the Big Bang theory, which posits that the universe originated from a singularity, a point of infinite density, around 13.8 billion years ago. This singularity expanded rapidly in a process known as cosmic inflation, leading to the universe's rapid expansion and cooling. The formation of matter, the creation of galaxies and stars, and the distribution of cosmic structures followed in a relatively orderly sequence, guided by the fundamental forces of nature. But while this framework has proven incredibly successful in explaining many of the large-scale features of the universe, it also leaves us with profound questions that remain unresolved. One of the most intriguing mysteries of modern cosmology is the nature of dark energy. Dark energy, which is thought to make up around 68% of the universe's total energy content, is responsible for the accelerated expansion of the universe. Despite its immense influence, dark energy remains largely invisible and its exact nature is unknown. Scientists have speculated that dark energy could be a property of space itself, a form of vacuum energy that permeates the universe. Others have suggested that it could be a manifestation of a new force, one that operates on the largest scales of the universe. The fact that dark energy is so pervasive yet so elusive highlights the limits of our understanding of the fundamental forces that govern the cosmos. In addition to the mystery of dark energy, there is also the question of dark matter. Dark matter, which makes up around 27% of the universe's total mass energy content, exerts a gravitational pull on visible matter but does not emit, absorb, or reflect light. Like dark energy, dark matter is invisible to telescopes, and scientists have been forced to infer its existence through its gravitational effects on galaxies and galaxy clusters. The discovery of dark matter has revolutionized our understanding of the universe, but it also raises new questions about the fundamental nature of matter itself. What is dark matter made of? How does it interact with ordinary matter? And why is it so much more abundant than the matter we can see? The interplay between dark energy and dark matter is central to understanding the evolution of the universe. Dark matter acts as a kind of scaffolding, providing the gravitational pull that allows galaxies and galaxy clusters to form and remain intact. On the other hand, dark energy is responsible for the accelerating expansion of the universe, pushing galaxies farther apart over time. The balance between these two mysterious forces will determine the ultimate fate of the cosmos. Will the universe continue to expand forever, driven by dark energy, or will gravity eventually overcome dark energy, causing the universe to collapse in a big crunch? Or is there yet another possibility, one that we have yet to fully comprehend? These questions remain at the forefront of cosmological research, and new discoveries may one day shed light on the fate of the universe itself. While the study of dark energy and dark matter has revealed much about the universe's composition, there is still much we don't know about the origin of these phenomena. The early moments of the Big Bang, just fractions of a second after the birth of the universe, remain a mystery.